So you want to mine an asteroid. It sounds like science fiction, like something from a movie with big spaceships and grizzled heroes. But it's a real idea. People are spending serious money trying to figure out how to do it. The question is, what would it actually take? Not in a movie, but in the real world with real physics and real budgets. It's a huge question, and the answer is complicated. It's a chain of problems, and you have to solve every single one of them in order. If one link in the chain breaks, the whole thing fails. First, you have to ask why. Why go through all that trouble? The answer is simple. Asteroids are full of stuff we need. And not just here on Earth. The real value is what they offer for expanding our reach into space itself. This Earth is at the bottom of a deep gravity well. Every single thing we send into space, every satellite, every probe, every person, has to be blasted out of that well with massive, expensive rockets. It costs thousands of dollars just to put a water bottle into orbit. Imagine trying to build a city in space by launching bricks from the ground. It's a terrible way to do it. Asteroids are the solution. They are chunks of raw material just floating out there. They are leftovers from the formation of the solar system. They come in a few main flavors. You have the C types, which are carbonaceous. They're dark, like lumps of coal. They are full of water locked away in their minerals. They also have organic compounds. Not life, but the building blocks. Then you have the S types, which are stony. They're made of silicate materials and some metals, like nickel iron. Finally, you have the M types. These are the ones that get all the attention. They are metallic. They are basically giant flying chunks of metal, mostly iron and nickel. But they also contain a lot of the good stuff: platinum, palladium, rhodium, iridium. The platinum group metals. These are incredibly rare on Earth, but common in some asteroids. So the why is clear. Water is the most important thing out there, not for drinking, but for fuel. You can split water into hydrogen and oxygen. That's the most powerful chemical rocket fuel we know. An asteroid rich in water is a floating gas station. It means a mission to Mars doesn't have to carry all its return fuel from Earth. It can refuel in space. That single change would revolutionize space travel. The metals, like iron and nickel, are for construction. You can use them to 3D print tools, build habitats, or create radiation shielding. It's far easier to use metal that's already in space than to launch it from Earth. The precious metals, that's the long-term lottery ticket. Bringing tons of platinum back to Earth would be incredibly difficult and would probably crash the market price anyway. The real value is using those resources to build an economy in space. So, you're convinced. You want to go get one. The first step isn't launching a rocket, it's finding the right target. Space is big, really big, and asteroids are small and dark. Finding them is hard. We have ground-based telescopes that scan the sky every night, looking for little points of light that move against the background of stars. These projects like the Catalina Sky Survey or Pan-STARRS find thousands of them, but just finding a dot isn't enough. You need to know what it is. Once you spot a potential target, you have to characterize it. What's it made of? How big is it? How fast is it spinning? Is it a solid chunk of rock, or is it a rubble pile? A loose collection of boulders and dust held together by its own weak gravity. We can learn some of this from Earth. We can analyze the light that reflects off its surface. This is called spectroscopy. Different minerals reflect light in different ways, giving us a sort of chemical fingerprint. We can get a rough idea if it's a C type, S type, or M type. We can also bounce radar signals off it if it comes close enough. Radar can tell us its shape, its size, and how fast it's rotating. It can even give us hints about whether it's solid or a rubble pile. But all of that is just a guess from millions of miles away. Before you send a multi-billion-dollar mining rig, you need to be sure. You need to send a scout, a small robotic probe. We've already done this. Japan's Hayabusa 2 mission went to the asteroid Ryugu. NASA's OSIRIS-RX mission went to the asteroid Bennu. These missions were incredibly important. They were proof of concept. They showed we can travel to a tiny asteroid, orbit it, map it in detail, and even touch down and grab a sample to bring back to Earth. A dedicated prospecting mission would do the same thing, but for mining. The scout would get up close. It would map the entire surface. It would use its own spectrometers to get a precise chemical map. Where are the water-rich deposits? Where are the metal concentrations? It would study the asteroid's gravity field to understand its internal structure. Is it solid or loose? It would look for hazards. Are there big, unstable boulders? Does it shoot out little jets of dust and gas as it rotates in the sunlight? You have to know all of this before you can even begin to design the mining equipment. Choosing the right asteroid is half the battle. You want one that's close, in an easy-to-reach orbit that doesn't take too much fuel. You want one with a high concentration of the materials you need, and you want one that's not spinning so fast that it will fling your mining equipment off into space. Near-Earth asteroids, or NEAs, are the best targets. There are cosmic neighbors. Okay, so you've found your perfect rock. Let's say it's a C-type asteroid, about 500 meters across, rich in water ice, and in a stable orbit not too far from Earth. Now you have to get there. And not just with a small sample return probe, you have to get a whole industrial operation there. This is a logistics problem of a scale we've never attempted before. You can't use the giant chemical rockets we use to get off Earth for the whole journey. They are powerful but terribly inefficient. They burn through their fuel very quickly. For a long trip through space, you need something that sips fuel. The best technology we have for this right now is solar electric propulsion, or ion drives. An ion drive uses electricity from solar panels to create a weak magnetic field that accelerates ions, like xenon gas, out the back. The push is tiny. It's been compared to the force of a piece of paper resting on your hand. But it's constant. Over months and years, that tiny, constant push builds up to incredible speeds. NASA's Dawn mission used ion drives to visit 2 different bodies in the main asteroid belt, Vesta and Ceres. It's the perfect technology for hauling heavy cargo across the solar system efficiently. So, your mission wouldn't be one ship, it would probably be a small fleet. First, you'd launch the main mining rig from Earth. It would be a big, heavy robotic machine. It would unfurl its solar panels and slowly, patiently begin its long journey to the target asteroid, a trip that could take a year or more. You might also send a processing unit, a sort of floating factory that will refine the raw materials. Maybe a separate tanker vehicle to bring the finished product back, and this whole operation has to be robotic. Sending people is just too complicated and expensive for the first attempts. You need life support, food, water, radiation shielding. The mission mass would balloon, and the risk would be astronomical, so robots it is. But this creates another huge problem, the time delay. When your asteroid is on the other side of the sun, the radio signal from Earth can take over 20 minutes to get there, and another 20 minutes for the response to come back. You can't control a mining robot with a joystick from Houston with a 40-minute lag. Imagine trying to dig a hole when your commands are half an hour late. It's impossible. This means the robots have to be smart. They need a high degree of autonomy. You can give them a general plan, go to this location, drill a hole 10 meters deep, and analyze the contents. But the robot itself has to figure out how to do it. It needs to be able to see the landscape, identify the best spot to place its feet, operate the drill, and handle problems as they come up. If the drill bit gets stuck, it has to know how to fix it on its own. We're talking about very advanced AI. An AI that can make real-time, high-stakes decisions millions of miles away from any human help. We are getting better at this, with rovers on Mars, but an active mining operation is a whole new level of complexity. So your autonomous mining rig finally arrives. It has spent 2 years coasting through space. It is now floating next to a dark, lumpy potato of a rock spinning slowly in the void. Now comes the hardest part. How do you actually mine it? This isn't like mining on Earth. There is virtually no gravity. You can't just drive a truck up to the rock face. If your robot tries to push a drill into the asteroid's surface, the reaction force will just push the robot away into space. You're trying to operate heavy machinery on a frictionless surface. The first thing you have to do is anchor yourself. You have to become one with the asteroid. How do you do that? You could use harpoons. Fire-sharp projectiles that embed themselves deep in the rock, with strong cables attached. You could use drills, land on the surface with legs, and then drill your feet deep into the ground like ice screws. If it's a small enough asteroid, maybe you could even throw a giant net or a bag around the whole thing and cinch it tight. Whatever method you choose, it has to be secure. The forces involved in mining, drilling, and digging are powerful. If your anchor fails, your whole operation is lost. Once you're attached, the extraction begins. The method you use depends on what the asteroid is made of and what you're trying to get. For a rubble pile with loose surface material called regolith, you might just use a scoop or a bucket wheel excavator, like the giant machines used in strip mines on Earth, but much smaller. Scrape the loose stuff off the surface and put it in a container. This is the simplest method. It's basically what OSIRIS-RX did, but on a massive scale. If your target material is deeper down, or if the asteroid is, solid rock, you need to drill. This could be a traditional rotary drill, or maybe something more exotic, like an auger that pulls the material out as a drill. The problem is what to do with the cuttings. In zero-G, they will spray out everywhere, creating a cloud of dangerous, high-velocity dust that can clog mechanisms and sandblast your equipment. You need some kind of shroud or vacuum system around the drill to contain the mess. For a metallic M-type asteroid, you could try something different, a magnetic rake. If the surface is covered in loose metallic rubble, you could just drag a powerful electromagnet across it. The metal bits would stick to the magnet, and you could then deposit them in a collection bin. Simple and effective, assuming the conditions are right. There's an even more futuristic idea for C-type asteroids rich in water and other volatile compounds. It's called optical mining. The idea is to use a large array of mirrors to focus sunlight onto a single spot on the asteroid surface. This concentrated solar energy would heat the rock to hundreds or even thousands of degrees. The water, ice, and other volatiles trapped in the rock would turn directly into gas. You would have a tent or a dome over the area to capture all this gas. The gas then gets piped away and cooled, separating out the water and other useful materials. The advantage is that there are very few moving parts, no drills to break, no scoops to get jammed. You're just using the sun's own energy. But no matter how you get the material, you're now faced with the next giant problem of raw, unprocessed asteroid rock. You can't just haul all of that back to Earth or to Mars. That would be like a logging company shipping whole trees with branches and leaves and all across the ocean. It's incredibly inefficient. You need to process the material right there, in space. You need to separate the good stuff from the worthless rock. This is called in situ resource utilization, or ISRU. Let's say you're after water. Your scoop has collected a ton of C-type regolith. You would dump this material into a big oven. You heat it up. The water trapped in the clay, like minerals, boils off as steam. You capture the steam and run it through a condenser, where it turns back into liquid water. And voila, you have water. You can then use electrolysis, running an electric current through the water to split it into pure hydrogen and pure oxygen. You store these in cryogenic tanks. You now have rocket fuel. What about metals? This is much harder. On Earth, we use giant blast furnaces and complicated chemical processes to refine ores. Doing that in zero gravity is an enormous challenge. One promising idea is carbonyl metallurgy. For nickel and iron, you can react the crushed ore with hot carbon monoxide gas. The metals react to form a new gas called a metal carbonyl. The worthless silicate rock doesn't react. You can then pipe the metal-rich gas away into a separate chamber. In that chamber, you heat the gas even further. The metal carbonyl breaks down, depositing the pure metal, almost like 3D printing, and releasing the carbon monoxide gas, which you can then recycle to process the next batch of ore. It's a complex closed-loop system, but it's a way to get very pure metals without having to deal with giant vats of molten slag in zero-G. All of this processing generates waste, piles of dry, useless rock dust and gravel. You can't just let it float away. It would create a debris field, a navigational hazard for future spacecraft. You might have to bag it up, or maybe you could use it. This waste rock, or slag, could be compacted into bricks, or used as a loose filler for radiation shielding. In space, you don't throw anything away, so now you have your product. You have tanks full of liquid hydrogen and oxygen. You have neat stacks of iron and platinum ingots. What do you do with it? This brings us to the business model. There are two main paths you could take. The first path is the one everyone thinks of. Bring it back to Earth, haul those platinum ingots back, and sell them on the commodities market. The problem is, getting back to Earth is just as hard as getting to the asteroid in the first place. And re-entering Earth's atmosphere with tons of dense metal is incredibly dangerous. You can't just drop it. It would become a meteor, a man-made one. You'd have to load the material into specialized re-entry vehicles, small capsules that can survive the fiery plunge and land safely. This adds huge cost and complexity. And then there's the market issue. If you suddenly dump 100 tons of platinum onto the world market, a significant fraction of all the platinum ever mined in human history, the price would collapse. You might end up making your own cargo worthless. The second path is much more realistic and, in the long run, much more valuable. Don't bring it back to Earth. Use it in space. This is the real reason to mine asteroids. You become a key part of the in-space infrastructure. Your asteroid mining operation becomes the gas station and the hardware store for the entire solar system. A company that wants to send a mission to Saturn no longer has to launch a giant, fuel-laden ship from Earth. They can launch a smaller, lighter craft and then top off its fuel tanks at your orbital depot. This makes their mission vastly cheaper and more capable. Governments setting up a base on the moon or Mars would be your customers. They would buy your water for life support and for making fuel. They would buy your iron and nickel girders to build their habitats. You would be selling the most valuable commodity in space, the ability to do things without having to haul everything up from the bottom of Earth's deep gravity well. This is how you build a real self-sustaining space economy. It's not about making Earth richer with space metals. It's about making humanity a multiplanetary species by using the resources that are already out there. The first asteroid miners won't be shipping jewelry back to Earth. They'll be shipping water to a Mars-bound colony ship. This all sounds plausible, step by step, but there are still massive hurdles that are stopping us from doing this today. The first, and biggest, is money. The upfront investment is staggering. We are talking hundreds of billions of dollars, maybe even $1 trillion, to develop all the necessary technology, launch the missions, and wait the decade or more it would take to see the first drop of water or the first ounce of metal. No single company can afford that. It would likely require a consortium of aerospace companies, mining corporations, and governments all working together. And it's a huge gamble. The return on investment is decades away, and there is no guarantee of success. One critical failure, one software bug, one failed rocket launch, and the entire investment could be lost. The second hurdle is the technology. We're close, but we're not there yet. We need more advanced and reliable ion drives. We need to perfect the AI for autonomous robotic operations. We need to test and prove the mining and processing techniques in a real space environment. All of these are difficult engineering problems that will take years and billions of dollars to solve. We can't just repurpose Earth-based mining equipment. Everything has to be designed from scratch to work in a vacuum, in extreme temperatures, and in zero gravity. The third hurdle is legal and political. Who owns an asteroid? According to the Outer Space Treaty of 1967, no nation can claim sovereignty over any celestial body. It's considered the common heritage of all mankind, but the treaty is silent on whether a private company can extract resources from that body. It's a huge legal gray area. The United States passed a law in 2015 that grants American companies the rights to any resources they extract from an asteroid. Luxembourg did something similar, but there is no international agreement. What happens if an American company and a Chinese company both target the same asteroid? Who gets to mine it? There are no space traffic laws, no cosmic mining claims offices. This legal uncertainty makes it very difficult for investors to risk billions of dollars on a project. So what would it take to mine an asteroid? It would take a convergence of things. It would take a few more successful robotic precursor missions like OSIRIS-REx to build confidence and retire some of the risk. It would take continued advances in robotics, AI, and in space propulsion. It would take a massive financial investment from a patient group of investors who understand this is a long-term play, not a get-rich-quick scheme. And it would take international cooperation to create a clear legal framework for space resources, a law of the space sea that everyone can agree on. This isn't going to happen next year or even the next decade. This is a project for the mid-21st century. It's a slow, methodical process of solving one impossible problem after another. Finding the rock, getting to the rock, grabbing onto the rock, digging into the rock, processing the rock, and finally turning that rock into the fuel and building materials that will open up the rest of the solar system. It's one of the hardest things we could ever try to do, but it's also the next logical step. If we ever want to move beyond just visiting space and actually start living and working there, we have to learn to live off the land. And in space, the land is the asteroids.